All right, so more about sets. So we're starting to get used to the basic idea. When we have a set, we have to describe it in some way, and a set should be well defined. What that means is we can tell what is in the set and what's not in the set. Often, to keep track of that, we'll do a couple of different things. We should have be able to write a written description of the set. We should be able to list the elements of a set. And sometimes it's nice to draw a picture of the set. With the illustration, what we often do is draw what's called a Venn diagram. And a Venn diagram is typically a big rectangle, could be square. And inside the rectangle, we draw a circle and sometimes multiple circles for the set. So I could have, let's make a new set A, and inside A, I'm going to put 1, 3, 5, 7, and 9. And outside A, I'm going to put 0, 2, 4, 6, and 8. The rectangle of the Venn diagram is what's known as the universal set. It's everything you have to work with. And then within that rectangle, you define circles for sets that live in that universe. So in this case, my universe would be whole numbers less than 9. So my current universe, my universal set, and then in there, I defined a set A just by listing the elements, and sometimes I can do it a different way. So in this case, I could say A would just be the list, 1, 3, 5, 7, and 9. And again, the order you list them doesn't matter. I'm just used to writing numbers in order, so that's why I wrote them that way. I could describe how those numbers are related together. That's the written description. So I could also say it would be all whole numbers. Now I could say whole numbers less than, I guess that would be less than 10. My description of the universe was incorrect because I want 9 to be in there. Now I could say all whole numbers less than 10, but that's already in my universe. I don't have to, but there's nothing wrong with being redundant. So I'm going to say all whole numbers less than 10 that are, I'm going to say odd. Now, for someone to understand my set, to agree what's in the set and what's not, then they would have to understand a couple of things. So there has to be that mutual agreement. They would have to know what I mean by whole numbers. They would have to know what I mean by less than 10, and they would have to know what I mean by odd. And if they're not sure of any of those things, I would have to find a way to, tell them what a whole number is, tell them what it means to be less than 10, tell them what it means to be 9, or just say, oh, it's these right here. So a set is well defined in a couple of ways. One, we write out a description of it that makes it clear what is in the set and what is not. Or two, we just list the elements and say, hey, that's it. These are the things in the set. If it's not there, it's not in the set, and that's okay. So we have a list, we have a description, and we can try to draw a picture of it. Let's try another one. let's go with the same universe. So my universal set, whole numbers, less than 10. And let's stick with the same set A. A is in the universe, and those are odd numbers. And I'm going to make a set B. Those are going to be prime numbers. And I'm skipping my redundancy about whole numbers less than 10 because I've already said, hey, that's my universe, right? So in this case, B would be prime numbers that are in the universe, which means they have to be whole numbers less than 10. So I'm going to try to draw a picture of that with a Venn diagram. So we already drew A before. When we draw a Venn diagram with sets, often if there's multiple sets, we'll draw them so that they overlap a little bit. And sometimes that overlap will have stuff in it, and sometimes it'll be empty. But we usually draw it anyway, whether it's empty or not. So I'm going to say there's set A, and here's set B. And think about my prime numbers for a minute. Before I get to my picture, I think I'll list them. Prime numbers are numbers that have exactly two different factors. So 1 is not prime because you could say, well, you could factor 1 as 1 times 1, but those aren't different factors. So that's not prime. 2 can only be factored as 1 times 2. So those are the two different factors. So 2 is in here. 3 can be written as 1 times 3 with whole numbers. That's the only way to do it. So 3 gets to be in there. 4 is 1 times 4 or 2 times 2. So it's got more than 2 factors. So 4 does not get to be in there. 5 gets to be in there. 6 doesn't. 7 gets to be in there. 8 doesn't. And 9 doesn't either because 9 could be 1 times 9 or 3 times 3. So I guess I don't need a comma. Those are my prime numbers in this universe. My odd numbers, remember, were 1, 3, 5, 7, and 9. So when I draw the Venn diagram, I want to be clear that these sets share some numbers. And so those numbers would have to go in this overlap here. So in here, I will put 3, 7, and 5. Otherwise, B needs to have 2. So I can see inside B's circle, I see 2, 3, 5, and 7. All right, so I got all those guys in its Venn diagram. A, well, I've accounted for 3, 5, and 7. I'm missing 1. Got it. And I'm missing 9. Got it. And then if I want to complete my universe, and the universe is the whole rectangle, I just list whatever's not accounted for. So let's see, we have 1, 2, 3, we're missing 4. We got 5, we're missing 6, 7, missing 8, and then we have 9. So let's double check again. 1, 2, 3, 4, 5, 6, 7, 8, 9. Everything's listed exactly once. A has all of its 5 elements. B has all of its 4 elements, and there happens to be some overlap there in the middle. So Venn diagrams can be very useful to kind of sort out how sets are related to each other. And those relations are pretty important. And we'll take a look at that next. Big ideas here is that a set should be well defined. We can describe a set by either writing a written description of it, listing its elements, or draw a Venn diagram to illustrate what the set is. Now, all the sets that I've listed so far are what are called finite sets. So far, we've only explored finite sets. There's another idea in sets called infinite sets. And infinite means goes on forever. And the idea of infinite kind of came up when we were playing around with patterns in numbers when I count. So an example of an infinite set would be the counting numbers. I can't write them all down. I can start. We start counting at 1, and then 2, and then 3, and then 4, and then we just keep going on and on and on. And if somebody says, oh yeah, I learned the biggest number is 1 billion. And I would say, well, what about 1,000,000,001? Oh yeah, right. And someone else says, oh, I heard the billion was a quintillion. And what about a quintillion-and-1? So every time we name a number, we can always add 1 and make a bigger number. So ... means it just keeps going. There's no end. And so if somebody said, well, how many elements? What's the cardinality of the counting numbers? Let's call the counting numbers, we'll give them a capital N for their name. And the best we can say is it's infinite. And the shorthand for infinite is this kind of sideways looking 8. And that's the symbol for infinity. So most sets we can count and say there are 5 elements or 4 elements in the set, but there's some sets that just go on forever. Those are infinite sets, and infinite's kind of a strange number. So we'll get more on that in a minute.